Have you ever imagined a forest so small that it could fit on the tip of your finger? It is a world not of wood and leaf, but of shimmering, intricate crystals. These are not mere trinkets of nature. They are a marvel of human ingenuity called metal organic frameworks, or MOFs. Picture a tiny, perfectly formed crystal tree, its branches reaching out, not for sunlight, but to catch the unseen pollutants that trouble our world. This miniature marvel, born in the pristine environment of a bright laboratory, represents a new frontier in our quest to heal the planet. It is a structure of immense complexity and profound potential, a tiny sponge with an insatiable appetite for the things that harm our environment. These structures are almost magical in their design, appearing like delicate, geometric snowflakes under a microscope. Each one is a labyrinth of impossibly small pores and channels, a microscopic maze waiting for its designated target. The sheer surface area contained within a single gram of this material is astonishing. If you could unfold it, it would cover an entire football pitch. This immense internal landscape is what gives the MOF its power. It is not a solid, impassable object, but a highly organized and spacious framework, ready to welcome and trap specific molecules. It is a testament to the idea that sometimes the most powerful solutions come in the smallest of packages. The name itself, Metal Organic Framework, whispers the secret of its construction. Think of it as a sophisticated building set for the molecular world. The metal components act as the strong, rigid joints or corners of the structure, providing a sturdy foundation. The organic parts, often called linkers, are the long carbon-based struts that connect these metal joints, forming the walls and corridors of this tiny crystalline house. By carefully selecting which metals and which organic linkers to use, scientists can build these frameworks with extraordinary precision, tailoring the size and shape of the internal pores for very specific tasks. This ability to custom design these materials is what makes them so revolutionary. It is not a one-size-fits-all solution, but a highly adaptable tool. Imagine being able to build a cage perfectly shaped to catch only one type of molecule, while letting all others pass by unharmed. That is the promise of MOFs. They are like highly specialized gatekeepers for the microscopic world, programmed to identify and isolate particular substances. This precision allows them to work with remarkable efficiency, targeting pollutants with a level of accuracy that was once the realm of science fiction, bringing a new and hopeful light to our environmental challenges. To truly appreciate the wonder of a MOF, let us venture inside one of these crystal houses. The metal ions, zinc, copper, serve as the hubs, the central points from which the structure expands. They are the anchors, holding everything together with strong, reliable bonds. These metallic nodes are arranged in a repeating, predictable pattern, creating a sense of order and stability throughout the entire crystal. Every single pore, every single chamber within the framework is identical in size and chemical property, making the MOF a uniform and dependable material for its intended purpose. Connecting these metal hubs are the organic linkers, the bridges that span the gaps and form the vast network of internal spaces. These linkers are carbon-based molecules, the very same element that forms the backbone of life itself. They can be long, short, rigid, flexible, and can be designed with specific chemical features that act like molecular hands, ready to grab onto certain guests. The interplay between the metal nodes and these organic struts is a delicate dance of chemistry, resulting in a structure that is strong and porous, robust and spacious, a perfect little trap for unwanted particles. The result of this elegant assembly is a material that behaves like a super sponge. But unlike a simple kitchen sponge that soaks up water indiscriminately, a MOF is incredibly selective. The size of its pores can be tuned with atomic precision, making them just right to allow, for instance, a harmful carbon dioxide molecule to enter while blocking a slightly larger, harmless nitrogen molecule. This selective absorption, known as adsorption, is the core of their function. The pollutant molecules are not just physically trapped, they are often held in place by weak chemical attractions to the internal walls of the framework. This process is remarkably efficient. The MOF doesn't need to hunt for pollutants. It simply needs to be present where they are. As contaminated air or water flows through the crystalline material, the target molecules are naturally drawn into the vast network of pores, like iron filings to a magnet. The sheer number of available docking sites within the framework means that a small amount of MOF material can capture a very large quantity of a pollutant. It is a passive yet powerful system, a silent guardian working at a scale we cannot see, but whose impact can be felt across entire ecosystems. One of the most immediate and vital applications for these tiny frameworks is the purification of the very air we breathe. Our modern world, with its bustling cities and industrial activities, releases a cocktail of harmful gases into the atmosphere. Carbon dioxide, volatile organic compounds from paints and fuels. Imagine a filter fitted to a factory smokestack, not just catching soot, but selectively pulling out the carbon dioxide, allowing cleaner emissions to be released. This is not a distant dream. It is a technology being actively developed today. A clear example can be seen in the challenge of indoor air quality. Furniture, cleaning products, building materials, harmful chemicals like formaldehyde. A simple, unassuming filter containing a specially designed MOF could be placed within an air conditioning unit. As air circulates through the system, the MOF would silently and continuously trap these harmful molecules, pulling them out of our living spaces. The result is a healthier environment for families to live and children to grow. A simple change with a profound impact on our daily well-being, powered by these invisible crystal sponges. Beyond the air, MOFs hold immense promise for cleaning our precious water resources. Rivers, lakes, oceans, lead, mercury, persistent organic pollutants, microscopic plastic particles. Scientists can create MOFs whose internal pores are chemically tuned to have a high affinity for these specific threats. When this MOF material is introduced into contaminated water, it acts like a highly specialized magnet, attracting and binding only the harmful substances, leaving the pure water behind. Consider an oil spill in the ocean, a devastating event for marine life. A specially synthesized MOF, designed to be hydrophobic but oleophilic, could be deployed across the surface. This material would selectively soak up the crude oil, much like a sponge, but would not become saturated with water. Once full, the MOF material could be collected, and the oil could potentially be recovered by heating the framework, allowing the valuable MOF to be used again. This represents a far more elegant and efficient method of environmental cleanup, a targeted approach that minimizes collateral damage to the ecosystem. The versatility of these remarkable materials extends far beyond simply cleaning air and water. Cleaning air-water. Their incredible storage capacity makes them ideal candidates for holding clean fuels, such as hydrogen. Hydrogen. A challenge with hydrogen power is storing it safely and densely. MOFs provide a potential solution, acting as a lightweight, solid-state tank that can hold vast quantities of hydrogen gas within its pores. They are also being explored in medicine for targeted drug delivery. A MOF could carry a powerful medication directly to a diseased cell, releasing it precisely where it is needed, minimizing side effects on the rest of the body. The beauty of MOFs lies not just in their function, but also in their potential for sustainability. Many types of MOFs are regenerable. After a framework has become saturated with a pollutant, it can often be cleaned by applying gentle heat, or by a change in pressure. This causes the MOF to release the captured molecules. Those molecules can be collected for safe disposal or even recycling. The now empty MOF is refreshed and ready to be used again and again. creating a cyclical, low-waste system, in stark contrast to single-use filters. This reusability makes them a far more economical and environmentally sound long-term solution. As we stand here today, on the 10th of October 2025, we are witnessing the dawn of a new age in material science. These tiny crystal trees are more than just a scientific curiosity, they are a symbol of hope. They demonstrate that with creativity, care, and a deep understanding of the natural world, we can develop solutions to some of our most daunting challenges. They remind us that the most powerful changes often begin at the smallest scale, with an idea that grows, branch by delicate branch, into something that can reshape our world for the better. The existence of such clever tools, however, does not absolve us of our own responsibility. The journey to a healthier planet is a shared one. While scientists innovate in the lab, we can all contribute in our daily lives. We can champion and support the development of clean technologies like these. We can make conscious choices to reduce our own environmental footprint, to conserve resources, and to advocate for policies that protect our shared home. The story of the MOF teaches us a vital lesson. Even the smallest, most intricate structures can have a huge impact. Let us all strive to be like them, small wonders working together for a brighter, cleaner future.